This is the last part of the 7.1 notes. What is a sampling distribution? So in these notes, we're going to talk about describing sampling distributions, and it's similar to some of the aspects you might have used in Chapter 1. So the first part here says the fact that statistics from random samples have definite sampling distributions allows us to answer the question, how trustworthy is a statistic as an estimator of the parameter? For example, how trustworthy is the sample mean as an estimator of the population mean? Turns out it's pretty trusty in most cases. To get a complete answer, though, we consider the center, spread, and shape of the sampling distribution. And right there, there's an example graph of a sampling distribution of a sample proportion. So just as a reminder, why are we doing all this stuff? Remember, we take our sample statistic, which could be a sample mean or a sample proportion, and we use that to estimate or make an inference about the population proportion. And what is a sampling distribution? Well, we could try to simulate them. It's if we took every possible sample and found the proportion for each one or found the mean for each one, and then we graphed the data. That's a sampling distribution. So let's start with this really important distinction. Biased estimators versus unbiased estimators. Unbiased gets the green because that's good. Biased gets the red because it seems to be bad. So in the chips example, we collected many samples of size 20 and calculated the sample proportion of red chips. How well does the sample proportion estimate the true proportion of red chips? P equals 0.5. So P, that's our true population proportion. And it was actually 0.5 for the proportion of red chips. So that was from the previous notes also. So this picture actually goes along with this. We collected many samples, so you can think about everyone in the class making a dot plot and then doing that over and over again. And it turns out, where's this thing stacked up at? The mode, the mean, the median, they're all stacked up at the true population parameter of 0.5. Well, that's going to end up being really important. It says, note that the center of the approximate sampling distribution is close to 0.5. In fact, if we took all possible samples of size 20 and found the mean of those sample proportions, we'd get exactly 0.5, which is what you might expect. The true proportion of chips was 0.5. So in green here, a statistic used to estimate a parameter is an unbiased estimator. Okay, so when is it good? When is it an unbiased estimator? If the mean of the sampling distribution, so you can kind of, it says close to 0.5 here, the mean would be about 0.5 for this distribution, is actually equal to the true value of the parameter being estimated, which in this case, the true proportion of red chips was 0.5, and our sampling distribution, right, hands-on, all those samples, ends up being centered at 0.5. So we can say that P hat was an unbiased estimator of the true proportion of red chips. So to summarize, what's an unbiased estimator? What's a biased estimator? Let's start with the bad one here. What would a biased estimator do? Well, it would consistently be too low or too high. So a biased estimator wouldn't be centered on the true value. It would be centered above or centered below because all of its values in the simulation, they'd be stacking up elsewhere, not on the true value. So the technical definition, you'll see it stated as being systematically over or underestimating. So if something's a biased estimator, it is systematically over or underestimating the true proportion. And then an unbiased estimator, that's the good one. So that gets green. What is an unbiased estimator? Well, basically it's just centered exactly where we want it. It is centered, like if you think about this distribution, where is it centered? It is centered exactly where the true population parameter of 0.5 is. So an unbiased estimator is centered exactly where we want it. So we should add that in here. Unbiased, an unbiased estimator, like P hat in this case, is centered at the true population parameter, which was 0.5 for the red chips. That doesn't mean it has to be perfect, right? Especially when we're running simulations, right? This doesn't look perfect, but still it's centered where we want it. So unbiased doesn't mean perfect, but it is centered where we would like it to be centered. Okay, let's talk about the spread of these things. So you can see this distribution or this distribution. One obviously has a bigger spread than the other. In general, low variability is better. So that would mean less spread. It says to get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. Great job. So that's centered exactly where we want it, over the true population parameter. This ensures that you won't need to overestimate or underestimate. Okay, but then we can improve on that. It says, unfortunately, being an unbiased estimator is no guarantee that the value of your statistic will be close to the actual parameter value. So again, we can still take an unbiased estimator. It's centered correctly. But that doesn't mean that when you take your actual p-hat, if you're a kid in the class, you took your p-hat, that doesn't mean that you're actually on 0.5, right? For example, this one might be centered correctly. So this one, 0.37, whatever this distribution is, this might be centered correctly. But if you're a kid in the class, there's so much variability that you could end up definitely off the true population parameter. So both of these distributions would be unbiased. They're both centered at 0.37, great job. But one is definitely better than the other. And what makes it better? Why is this one? I mean, you can see that the spread is much smaller for this one. You'll notice n equals 100. So this must have been when the kids were using 100 as the sample size. This one was n equals 1,000. So if we're using 1,000 as the sample size, you can see how much it decreases the variability. So the point is this. Why do we say low variability is better? Well, because look at how this is squeezed down to just this region. So our estimates are definitely improved. So the point is, if we increase sample size, we decrease variability. They're both centered in the right place, but this one allowed for a lot more variability. So we could still, if we took an individual sample, we could end up anywhere in here. This one squeezed it way down, squeezed that spread way down. So if we take an individual sample of 1,000, we have much less room for variability. So overall, that makes our estimates more consistent. So the big takeaway here, larger samples have a clear advantage over smaller samples. They just have much less variability. Doesn't mean that this one's not stacked up in the right place. Doesn't mean that this one's not unbiased, right? But you can see that the larger sample, it just decreases the variability. So continuing with that thought, they are much more likely to produce an estimate close to the true value of the parameter. There are general rules for describing how the spread of the sampling distribution of a statistic decreases as the sample size increases. And that's what we just looked at with that diagram. The spread decreases when the sample size increases. One important and surprising fact is that the variability of a statistic in repeated sampling does not depend very much on the population size. So something we haven't considered yet. What about the size of the population? What if it's a smaller population? Or what if it's a huge population? So we actually have a rule for this, and as long as it doesn't break this rule, the size of the population itself really won't matter. Now, the sample size we just saw, that could make a big difference in the sampling distribution. But the population that these samples are coming from, again, as long as we just follow this rule, we'll be good. So it says the variability of a statistic is described by the spread of its sampling distribution. So remember, if we stack up all the X bars from each kid or stack up all the p-hats, that's our sampling distribution. The spread is determined mainly by the size of the actual sample taken by each kid. Larger samples give smaller spreads, right? We just looked at that. The spread of the sampling distribution does not depend much on the size of the population. That's the thing that might come as a surprise to you. As long as the population is at least 10 times larger than the sample. So let's take a moment. 10 times larger than the sample. So that's the rule in terms of the population. As long as we don't break that, we're good. The population size otherwise doesn't really matter. There's just a certain threshold for the population. It has to be at least 10 times as big as the sample. Okay, the next part here, how can you reduce the variability of a statistic? Basically, how can we squeeze down that sampling distribution? I think the big takeaway, increase the sample size. So right now, statistically, that's all I've got. How do you reduce the variability? Make the sample size bigger. There is one thing I want to point out from Chapter 4 that as a statistician designing the study, you could do to improve it. Maybe you could just review and consider improving your design, in the sense that maybe you want to run a stratified sample. So that's just a little side note from Chapter 4. How could I make my study better? Right? How could I reduce the variability somehow on my end? Well, maybe you just improve the design. So maybe you want to do a stratified sample so you can decrease the variability in your results. So that's why that one's in parentheses, is because that's just a little side note from Chapter 4 that you could always consider as a way to reduce the variability. And this piece right here, what effect does the size of the population have on the variability of a statistic? And we just answered that. It actually doesn't have much, right? It has very little effect. It has very little effect. So the population size is capital N. And we can write it symbolically. We can just say, as long as the sample size, little n, is less than or equal to 1/10 of the population size. So we really don't care much about the population size. All of our statistics will still be good as long as our sample size is less than or equal to 1/10 of the population size. And that's really saying the same exact thing as the population is at least 10 times larger than the sample. All right, and the last part for these notes, bias, variability, and shape. It says we can think of the true value of the population parameter as the bullseye on a target and of the sample statistic as an arrow fired at the target. Both bias and variability describe what happens when we take many shots at the target. So we've got 4 possible scenarios here. Bias, in this case, with our targets, means that our aim is off and we consistently miss the bullseye in the same direction. Our sample values do not center on the population value, which in this case, the goal would be the bullseye. And then high variability would mean that repeated shots are widely scattered. So repeated samples do not give very similar results. They're kind of all over the place. So this one is a high bias. It's far from the bullseye, but it's got very low variability. So definitely not an ideal example if that's our sample statistic, right? If it's always off the true population parameter, it would be biased, even though it's got low variability. And then B here, this appears to be unbiased, right? If we averaged all of these out, their position, they would probably average out to about the bullseye. So that's unbiased. But you notice how far spread apart they are. So it does have high variability. So yes, it's unbiased, but the variability is really high, so also not ideal. And then C, I think this is the worst one. It's definitely not unbiased, right? Unbiased would put us around the bullseye. So the fact that this is off the bullseye, this would be biased. And the fact that it has a decent amount of spread, it doesn't have low variability either. So high bias, high variability. This is the worst example, right? This would be the sample statistic that we wouldn't want to use. And then D here, this is definitely the winner. You can see they're all centered around the bullseye. And not only that, it's improved on this one. It's improved upon that because we have low variability. So we're centered at the place we want to be. We're unbiased. And we have a tight grouping, so we have low variability. So this guy, D, is definitely the winner here. Okay, and then the last part here, what's the difference between accuracy and precision? How does this relate to bias and variability? Because in our case, accurate has to do with one of these, either bias or variability, and precision. So if you had to match them up, which one would be which? Well, if you'll notice, the ones that are accurate would be the ones that are getting close to the bullseye. So which ones would actually be going at the bullseye where we want it to go would be these two. So notice, these are the ones that don't have any bias. So if you're unbiased, that would mean you're accurate. Well, then precise would have to be the consistent grouping. That would have to be the low variability. So in this case, accuracy would mean we're dead on, that's where we want to go, that's our target. So accuracy, that's the unbiased case. Like this one, wow, very accurate. You're right on the bullseye, so you're unbiased. And this one, although it wasn't all on the bullseye, they're centered around the bullseye. If we average them out, they should be on the bullseye. So this one you could also say is unbiased. So those are accurate. They're getting at the bullseye. So centered at the true population parameter is what we're interested in. That's unbiased. And in this case, that also relates to the accuracy. Okay, then precision must be the other one. Precision must have to do with the variability. So if we're precise, right, if we're precise, we like to be precise, that would be low variability, so the tight grouping. So looks like A, tight grouping, D is a tight grouping. So precision has to do with being consistent. So to be precise, in this case, means to have low variability. Like example A, that's really precise, although it's biased, right? It's off the mark. Or D, which was really good because not only was it precise with a tight grouping, but it was unbiased. It was right on the mark where we wanted it to be. So we've talked about what makes a biased versus an unbiased estimator. And our estimator is a sample statistic trying to estimate the true population parameter. And we've also talked about how to decrease variability within the sampling distribution of our statistic. And in general, we just need to increase the sample size. And then one final note, the size of the population doesn't really matter as long as it's 10 times larger than our sample. So that is it for these notes. I'll see you in class.